have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night. But we continue to search. We can't help it. A central element of the human future. If we crave some cosmic purpose, then let us find our
Hello, and welcome to another episode of NASA Science Live, an opportunity for you to interact with NASA experts and have your questions answered live on air. I'm your host, Tahira Allen, and today we are joining you live from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We will be taking your questions about Webb's historic images all throughout today's show, live on air. For those of you tuning in on social media, you can use the hashtag #UnfoldTheUniverse to submit questions or drop your questions directly into the comment box wherever you're watching this stream. This week, the James Webb Space Telescope released its first full-color images and data. And this is just the beginning. As the world's most powerful space telescope, it will examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, planets, and the evolution of our own solar system. This is a huge moment, marking a new way to see the universe beyond where we have ever been, beyond time itself. Let's take a moment to pull back the curtains and see what Webb has revealed. This first image of a galaxy cluster takes us back 4.6 billion years, giving the deepest and sharpest infrared image of the distant universe to date. This graph, the most detailed of its kind, shows the distinct signature of water in the atmosphere surrounding a hot gas giant planet that is orbiting a distant sunlight star hundreds of light years away. In this image of the Carina Nebula, Webb peers through cosmic dust, revealing previously invisible areas of star birth. Covering about 1/5 of the moon's diameter, this is Webb's largest image to date, showcasing in rare detail a group of interacting galaxies known as Stephan's Quintet. And some stars save the best for last. Webb captured a dying star's final performance, sending out rings of gas and dust for thousands of years in all directions. So now that we have seen these incredible images, let's talk to our experts. I'm joined today by Dr. Alex Lockwood, Webb project scientist, and Dr. Nestor Espinoza, Webb astronomer, both from the Space Telescope Science Institute. Thank you both so much for being with us.
Thanks for having us.
Thanks to hear.
So the big day is here. We've seen the images. We have the first data. Nestor, I'm going to start with you as our astronomer. Can you talk through what Webb's new images show us that we weren't able to see before?
Well, Webb is revealing a universe to which we were a little bit, it's invisible for us, right? It's looking in eyes that we don't have, in colors of the light that we are not able to grasp. But right now, thanks to this beautiful machine, we're able to see the birth of stars in ways we've not explored before. You know, galaxies far, far away, and even distant exoplanets with impressive detail. So, you know, I'm beyond stoked to be here talking with you about this.
Yeah, absolutely. And you mentioned seeing in colors that our eyes can't see. Webb has this ability. What's so great about that? Like, what do those colors show us about the universe?
Right, depending on the physical process that you're looking at, it can give you a ton of information. For instance, let's look, you know, my expertise is in exoplanets, so of course I'm going to go back there. Yeah. And for exoplanets, the infrared holds the hidden molecules that are the most important for us. When you hear water, when you hear carbon dioxide, when you hear methane, all those molecules are hidden in the infrared, and that's why we have to go there. That's why I'm so excited to see all this flow of data through these images that we can explore together.
Absolutely. And so we have this clear view. We know that the instruments are working. Alex, as the project scientist, can you shine light on how Webb will take humanity's knowledge of the universe to the next level?
Well, it's really it's complementary to what we've seen with a lot of the telescopes, especially Hubble. Hubble does visible wavelengths and infrared, and James Webb does infrared. And it's kind of like if you look at the human body. We can see a body, we see people every day, but you go to the doctor's office and you get an x-ray and you can see your bones, you can see what's inside someone. And it's very different than what you see when you're looking at the person, but it tells you a lot more information, and it's complementary. It's the same thing. James Webb it's not an x-ray telescope, it's an infrared telescope, but it's the same idea that it gives us a completely different but very informational view of things that we've already seen with Hubble and things that we have yet to see.
Amazing. And so it's my understanding too, like this is just the start for Webb. So these are just the first images and the first showcasing of its capabilities. So Alex or Nestor, can y'all give us an idea of what images and data we can expect in the first year of science?
Yeah, absolutely. There are lots of programs that are scheduled from astronomers across the world. I think there's over 40 countries that people have gotten data that they're going to get data from. And we're going to see more images like the deep field that we saw yesterday. People are going to study that, but fields like that for even longer to find even more distant galaxies. Lots of time to do that. In fact, I think that program is running as we speak. A program like that. We're going to look at more exoplanets, which Nestor can tell you all about. And we're going to look at star-forming regions, understand star birth, and star death, like one of the images that we saw of the southern ring. Really, Webb spans the gamut of anything astronomical, and we have all of that planned in the first year. It's really, really great depth.
Yeah, if I might add, the most exciting to me, at least as an exoplanet person.
Yeah.
Webb is the first observatory that will allow us to explore worlds as small as ours. And these observations have already happened, some of them actually, and they're going to be explored by scientists starting tomorrow. And we're going to start learning about these worlds outside our solar system for the first time with exquisite detail. I don't know what we will see. We have some idea, of course, but the universe keeps us surprising us, and that's what I'm most excited about, the unexpected.
That is amazing. And so it wasn't the WASP exoplanet that we characterized the atmosphere. That was light years away, wasn't that?
It was 1,000 light years away. It's very, very far away. But even though it's so far away, Webb has such a huge mirror and such precise instruments that we can see, water features that you're seeing right now with exquisite details. I don't even have to show you a model. You can see the wiggles going around. Each of those wiggles, it's water vapor in the atmosphere of this exoplanet 1,000 light years away. Imagine what we can do with this.
No, seriously, that's why I'm getting so excited. Like it's crazy to think about and just to wonder what is going to come next. This is amazing. This is so exciting. And we have so many questions coming in online. So I'm going to take a pause and we'll take some questions from our viewers. As a reminder to those tuning in, you can submit questions for our experts on today's show by using the hashtag #UnfoldTheUniverse on social media or by dropping your question directly into the comment stream wherever you're watching from. So, our first question is from Charlie on Twitter, who asks, does anyone know if Webb has the ability to view objects within our own galaxy?
Yes, definitely. Well, a lot of Webb's bread and butter is distant galaxies outside our own Milky Way. Most of the star-forming regions and planetary nebula, like we saw yesterday, and the exoplanets, all the exoplanets that we can study are actually within our own galaxy. We can see very far because of Webb's big mirror and sensitive instruments, but the closer we are, the more detail we can have. So something like this beautiful nebula that you're seeing right now, that's within our own galaxy, and we can see a lot more details and see inside the nebula to see what's going on.
So we can see within our own galaxy. Can we see within our own solar system?
Yes, we can. We have observations in the first year, as we were talking, to look at objects from Mars all the way out to the Kuiper Belt in our own solar system. Yeah.
I mean, that's amazing. That's really exciting to think about. It's going far. It's going close to home. It's it's going to be great. And so let's move on to Nick from Facebook, who asks, can the JWST be pointed towards an exoplanet and get a clear image of it? Nestor?
Well, actually, part of the observations that are going to be made, it can get what we call a direct image, which is really like a little blob in a plot, so you won't be able to see these artistic representations that you typically see from these exoplanets. But we can get direct light from some very young, hot, and distant exoplanets out there. So there's some modes. In particular, there's one mode that it's called a coronagraph, which is like, when you're in the street and there's too much light and you put your fingers on top so you don't get, too much light on top. Mm-hmm. That's exactly what we're doing with the star that the planet orbits. So we try to block it with a little needle, basically, which we have some ways of doing it on board. And we're able to see like a little dot going around, and that's the planet. So yes, there will be some observations of that with Webb, which is quite amazing on its own.
Yeah, and what does the coronagraph tell us?
Well, the coronagraph actually tries to remove the star, because the whole point, and this is very interesting to think about, we're able to get light from the farthest away galaxies, right? So very, very faint things. People always ask like, well, how can you not get an image from a planet? They're closer, right? The problem is the star. The stars are so bright that you cannot just see like the faint point of what is the planet right on top of it. So you have to remove it somehow, and these coronagraphs just remove the light from the star, so you can have a pristine look at the planet. That's a little dot.
Okay, cool. That's so interesting. And so Claire on Twitter asks, how does JWST know where to zoom in to capture the images?
That's a good question, and that is actually decided by astronomers worldwide. Every year there's a process of selecting the targets, very rigorous. Lots of astronomers get together and look at the proposals without names on them, so they're unbiased, and they say what's the best science for Webb to do. And then once those targets get chosen, then we put them into our calculators on Webb, and we point Webb. But where it looks specifically at any given time is based on the science target, and those are proposed by astronomers across the world.
Nice. And isn't Webb just very efficient? I know we were talking before that it's really kind of making it a little easy on astronomers right now. Could any of y'all talk to that?
Maybe, yeah, I can jump into that. I mean, the way in which you get from the data to the results, it's incredibly fast. This is a story that we both were part of within producing these very first images. Like the analysis of the exoplanet, in one day we have like one spectrum already. So in one day, these things, with previous instruments, they took like years, like tens of years even for some instruments. But now Webb, it's so stable, it produces data so pristine that you're able to extract information right away from it. So that speaks of its efficiency at observing how the data is reduced, etc. So it's gonna open up, it lowers the bar so people can jump and do science on their own, much faster, much quicker, and much more efficiently. So
yeah, and I'll add that deep field image that we saw with all the galaxies in it, that was taken in less than 12 hours with Webb, and a similar image that wasn't as sensitive took over 100 hours with Hubble. And so you're talking about 10 times faster to get even more data. That's really good efficiency.
I think it's safe to say that it was worth the wait.
Yes.
Webb is doing some great things. So moving on, we have Holger on YouTube who asks, what interesting observation is planned of objects within our solar system?
Yeah, that's a really good question. So we are going to look at, just like we're studying with exoplanets, the atmospheres. We're going to look at the atmospheres of planets within our own solar system, the ice giants and the gas giants. There's a lot of beautiful cloud structure in Jupiter and Saturn that we're going to study, as well as the moons of those planets, to understand the entire system more. And again, look at these molecules that Nestor was referring to, methane, carbon dioxide, that are very strong in infrared wavelengths.
So I actually have a really good follow-up question to that. On Parith Viraj on YouTube asks how these photos are useful for space scientists and other scientific communities. So while we do get this data, I guess, could you talk a little bit about how it might be applied?
Sure. Yeah. So these images actually, whenever you're seeing these beautiful colors on these images, you're reading physical processes happening in them. And this is the first deep field image. One of the important bits on this, you can see a star there, like the brightest dot there. That's a star. But you can see that why don't we capture so many stars as well is because this is such a tiny image. I mean, that's impressive. You know, it was said when the person was showing up this, that it is like as small as a grain of sand, you know, projected on the sky. So that, you know, that speaks wonders of what you can get out of this. But yes, stars do photobomb like galaxy images, but you know we know how to deal with them.
And the closest star, we built a giant sun shield to block that light.
Yeah.
So
The sun, yes, of course.
That's funny. So Emma on Twitter asks, "Hey NASA, I was wondering what's coming next. What are the next targets for Webb, and how often will we be surprised with new images and data?"
that's a good question. Well, I can tell you that during this week, they have been looking at some of the deepest galaxy fields and some of the rockiest planets. So really, in the past couple of days, they have spanned the gamut of science and distance. And you can anticipate new data and images definitely within the next few weeks. And then I would say that every month at least Webb is going to surprise us. There are already astronomers out there who have taken data that was released today and are starting to analyze them and figure out the amazing scientific results. And so you won't have to wait long. I can say that.
Okay. I mean, that's great. That sounds good to me. I'm sure with everybody else. And so we've waited long enough. So you said that Webb's targets have spanned the gamut, spanned all across the universe. Has it captured anything in our solar system already?
Yes. So actually, during the 6-month commissioning process, there was an image taken of Jupiter to test some of the modes to make sure that it wasn't too bright, to make sure that we could track Jupiter as it moves across the sky, because objects in our solar system move much faster relative to distant things. And so those were successful images, and you can see them here. Successful doesn't even say anything because they're beautiful. So as we said, we're going to study objects in our solar system, and for Jupiter, one of the very interesting things is the clouds and understanding the cloud structure, which pops out clearly in one of these images. And so this data itself just came out today, as all of the data from the past 6 months was released publicly today.
Great. And so we have Marcia on Facebook who asks, there are more than 5,000 known exoplanets, and being able to provide spectroscopy at the level of Webb is outstanding. How many of those exoplanets are scheduled for observation?
Oh, that's a good question. In the first year, I remember the list was in the several tens, at least within now. And that there's a beautiful picture that was made by Nicole Colon from NASA, showing the whole span. It covers the span from rocky planets. In fact, one of them, perhaps one of the most exciting ones, TRAPPIST-1 system. We can speak more about that later. But that one hosts some planets that might be in the habitable zone, and this system was already the observations are already there. They're already taken by Webb. They cover all the range from rocky planets to giant planets, hot, cold, you name it. All the diversity is out there in this first year, so I cannot wait to see what comes out of this.
I mean, your energy is like, I can feel it right now, so I'm very excited about this as well. Overview Effect on Twitter asks, what was the exposure time of the released images, and how does the Webb's deep field compare to Hubble's ultra deep field?
Yeah, so each of these images, it depends on the image, but yeah, you can see the beautiful comparison with Hubble's image of the same field and Webb's. And as I mentioned before, this image of Webb took, I think it was total 12 hours, and the Hubble field took days. So really a very large difference for time that it took. For the other images that were released yesterday, they were all between 6 and 12 hours apiece, depending on the image. And yes, Webb is just as powerful as Hubble, And I think these images really show that they're complementary, and Webb has the beautiful resolution and added detail.
I mean, it's amazing. It's like going to the eye doctor and getting your glasses updated. You know, you can see clearly now, and this is incredible. So, Nestor, I've got a good one for you. Wild Dogs OG on Twitch asks, I wonder why NASA looked at WASP 96b first instead of Proxima Centauri or Alpha Centauri or even TRAPPIST-1.
That's an excellent question. First of all, the Proxima and Alpha, they're too close, they're too bright, but we'll find ways to figure those one out.
Okay.
But WASP 96b is a very, very interesting planet on its own. So the story goes that when we look at other exoplanets with Hubble, whenever we look at a hot giant exoplanet, we find clouds. And we actually, that's no surprise if you, like in retrospective, that was no surprise. Because when you look at the solar system, all giant planets have clouds. But then this one, the features that Hubble was seeing, and also ground-based telescopes were seeing, are so distinct that there was this belief that maybe it didn't have clouds. And that was very weird. Like I was personally weirded out by this. So, NASA made the excellent selection to go with this planet to figure out, what we will see with Webb size. And guess what we found with Webb size? Clouds. Yes, we found like some very, very distinct signatures of clouds. So if you look in detail, with a detail as precise as what Webb Ice presents to us, you actually found things that you believed that they were not there before. And that was exactly the case with WASP 96b. So I think it teaches us a lesson. And I tell you, we have people from the scientists right now trying to figure out all the little details, trying to model the data from the picture that we released. So it's exciting on its own. It's a very, very exciting system.
It is exciting, too, to just hear that we have learned something that we didn't expect in just the first observation. Again, This is just the start. And so that is incredible to think about. So we have Tara Blakeham on Twitch who asks, what were your thoughts and reactions when you saw the colorized pictures for the first time? What did that feel like?
When the first image was taken of the Carina Nebula, which is that beautiful landscape that we saw yesterday, the first image, just one color of the image, was available. We immediately downloaded it and just looked at the raw data. And I literally teared up because there was so much structure just in one color. And you can see it in the image. The structure equals scientific potential, because those details are where you extract all the nuance in the story and the science. And I teared up. I could not believe how good Webb was. Better than expected. It's been really emotional.
I can imagine, Nestor.
Yeah, no, I had the same. And the beautiful thing was seeing the process. The process of yes, you get color by color, and you start adding. It's like making a painting of the universe, right? And you're right there, sitting in this big table with these beautiful images just being made, and being these, amazing human beings next to you, being able to share that with the world later. It was a whole experience. So it was a very, people typically think that we scientists are very, very square. This was a very human experience of sharing, of amazing each other, of, just peering into the universe with these pictures. It was amazing. Yeah.
We sat in a room literally every day for the past month, a group of about 30 of us, scientists and artists, and looked at these data as they came down. And it was a privilege. It was amazing. And yeah, as Nestor said, it was a team effort, and the human element of trying to do the best by this mission, by, humanity, to really wow people. Webb brought it.
Yeah, absolutely. That's the best way to put it. So, Alex, Nestor, we will be back with you in just a bit to answer some more questions from our viewers. For those of you tuning in, keep sending your questions online. You can submit them using the hashtag #UnfoldTheUniverse on social media, or by dropping your question directly into the comment box wherever you're watching from. The Webb Space Telescope is just starting its science and still has so much to reveal about our universe. The newly released images have given us a never-before-seen view of the cosmos and reminded us how science and art are so beautifully woven together. As the telescope continues to peer into the great beyond, what do you think Webb will see? Show us by creating art. You can sing, you can dance, you can write, you can paint. In this case, the universe is literally the limit. Share a photo or video of you and your creation using the hashtag #UnfoldTheUniverse for a chance to be shared on NASA's website or social media channels. Need some inspiration? Let's take a look. All right, we are back with Dr. Alex Lockwood, Webb Project Scientist, and Dr. Nestor Espinoza, Webb Astronomer, to keep taking some more of your questions online. If you're just tuning in with us, be sure to submit your questions using the hashtag #UnfoldTheUniverse on social media or by dropping your question directly into the comment box wherever you're watching this stream. Yesterday, communities around the world were hosting special events for Webb's image release, and we received a video question from one student named Olivia, who is part of the Girl Scout troop of Tropical Florida. Let's take a look.
Hi, my name is Olivia Galvan, and I'm from Miami, Florida. And my question is, will the James Webb Telescope give us more information about the Earth's climate change?
Great question, Olivia. So, Nestor, Alex, what can Webb tell us about Earth's climate change?
Well, this is an excellent question, Olivia. Thank you very much. Well, the reality is that Webb has this promise, of being able to explore distant exoplanet atmospheres, even for the ones of planets that might host habitable conditions, maybe even similar to Earth. So that allows us actually to start peering into the diversity of atmospheres out there. And that actually teaches us, where maybe our atmosphere might end. And therefore, or how many other types of atmospheres end. And that can actually, inflow into our understanding of our own climate change here on Earth. Mm-hmm. Alex, what are your thoughts?
Yeah, well, to me, climate change is a really big question and a big challenge for humanity to take on. And that's actually just like Webb. 20 years ago, people had big, audacious questions about the universe, and then we built exactly the perfect, incredible tool to answer those. And it was an international collaboration. That's the only way that it was possible. And so I think, tackling Webb and tackling climate change are similarly audacious challenges, and we've proven we can do it. So I really think that gives us hope for the question of what we can do for climate change.
I mean, absolutely. Seeing what Webb has done, that leaves me hopeful. Yeah. So, that sounds great. Our next question is from Tesla Hype on Twitter, who asks, what might Webb teach us about dark matter or dark energy?
Well, these detailed images that you were just seeing about galaxies, there's some of them for which you can see such exquisite details as to, where certain populations of stars are hidden. Or, even some of the dynamics you will be able to see about these galaxies. That's the key for investigating dark matter, for instance. Dark matter is one of the parts that dominate the whole dynamics in these galaxies. And therefore, it will definitely tell us new clues about how dark matter is spread through different types of galaxies. There's even, the hypothesis that maybe some galaxies might not have a ton of dark matter, for instance, but those are very, very faint. But then Webb has such huge mirror that it can actually peer into those with very, very, enough detail to tell you, oh yes, maybe it doesn't have. So all these questions, yes, it will enable us to answer them. And in terms of dark energy, this strange thing that it's making in the universe to not only expand, but expanding in an accelerated fashion, like every second it's expanding faster. Because Webb can reach out to the most distant galaxies, it can actually teach us a ton about how this expansion happens at different positions, at different times even. So yes, definitely, it will allow us to peer into details that we have not had the chance to before, for sure. Yeah.
So one thing that I think is really cool is how we tend to use different telescopes. We use data from multiple different telescopes to get an even bigger picture of the universe. So will Webb be complementary to any of the other space telescopes that are already out there, or that might be coming up in the future?
Alex, you want to take this?
I mean, absolutely. You can already put Hubble and Webb images side by side, and you see that there's additional information that you can get from both of those images. And in terms of studying the scales of the universe and dark matter and dark energy that we were just talking about, the LIGO mission, the LIGO telescope that measures gravitational waves, it has found some incredible pairs of rotating neutron stars that helps us understand Einstein's original equations. Webb has the ability for when a unique phenomenon like that happens, Webb has the ability to stop what it's doing and go look at that to provide additional information. And there's actually a system between telescopes where they can alert each other to say, there's something really important and timely going on in the universe. Let's look at it together to get added information. And so Webb will be
cool.
part of that as well.
So telescopes can phone a friend, and oh my gosh, that's amazing. That is a fun fact. So Wait 1 Minute on Twitter asks, how do scientists separate stars from galaxies in such pictures?
Well, the structure tells you a lot about that, first of all. The fact that galaxies are, we have a name for them, diffuse sources or not. I can't remember actually now the word. But we know which sources are like galaxies or more diffuse, while stars are very, very pointy points in the images. There's a point, though, in which, especially for the faintest stars, in which it gets kind of tough to separate between them just from an image. So you have to go and get more data. There's a point in which it gets challenging, but for most of them, we have a pretty good idea on how to do that.
I actually have a great follow-up to that. So Aarononis on Twitch asks, how do you convert the data into such colorful photos?
Ooh, you want to take this?
Sure. The data come down, as ones and zeros. But basically, what you do is you focus on one color of light at a time, and on your infrared detector, you say how much light is being collected on any given point on the detector. And so you actually have a spatial map for where the light is coming in. And the more light you get, the brighter it is in that one wavelength and that one color. And then we take many color pictures, individual wavelengths, and then add them together to make color images.
It's a process on its own. It's a whole art. We have experts in-house back at Space Telescope that did all this, and seeing this work unfold, unfold the universe, was magnificent. How we humans can make this happen, these beautiful images, it's a whole process that I loved. Yeah.
It is, and I'm glad that you said that, and you alluded to it earlier about how Webb is truly an international mission. Didn't over hundreds of scientists and thousands of engineers work on this mission?
Over 20,000 people make this mission happen. So it's a huge team effort, right?
Mm-hmm. And now over the next year, there's over 1,000 people who are scientists who are going to use the data. And that's just people who already know they're going to use the data, and there's going to be a lot of more people who jump on it. It has only been possible with an international collaboration in all of these people, and it will, its legacy will extend, and the scientific discoveries will extend as more and more people, and really the next generation of scientists, take this on as their mantle.
Speaking of the next generation, we have Alex, who is 12 years old, who asks, what is the maximum distance that Webb can see?
Good name, Alex. So Webb, we anticipate that Webb is designed to look back about a light travel time distance of 13.6 billion years. so to within about 150 million years of the Big Bang. And it's hard to like put these numbers in perspective. Hubble has seen to about 400 million years after the Big Bang. And out of the age of the universe, which is 13.8 approximately billion years, Hubble has seen maybe like a 2-year-old out of the entire age. Webb is going to be able to see a 1-year-old or a 9-month-old. And Nestor and I have young children. We can tell you that there is a ton of change that happens between 9 months and 2 years. And so understanding the beginning of the universe is going to be, really, really amazing with Webb.
That is so exciting. And so our next question is from Tony Jebsen on Twitter, who asks, do we know how deep in the atmosphere of WASP 96b the clouds and haze are?
Yeah, actually, we have some calculations on that. I could tell you the pressure or the height, but I don't think it makes it's gonna make much sense to say it here. But we do, and that's information that it's embedded in this beautiful spectrum that you're seeing here. We know the exact location where the cloud actually starts. We know that it has to go below a certain pressure. So we know like a little bit of the structure of the atmosphere. So yes, that's the kind of information you get from modeling data like this.
That is so exciting. And so we have Megan Carroll on YouTube, who asks, regarding the fantastic image of the dying star, would the supernova of one star cause the destruction of the other? So I believe there are 2 stars in that image. And how large is that explosion?
So that's a good question. There are 2 stars in this image, and the one that you actually can see that looks brighter, that actually has the strong diffraction pattern, that's actually still alive and well. It's a hot star. The one that only really appears in the mid-infrared image, that's the star that has died. They do gravitationally exert a lot on each other, but the explosion, and in this case, it wasn't quite a supernova. It wasn't quite as massive a star enough to make a supernova. But the explosion from the death of the first star, the material will pass by the second star, but it's not going to perturb it. However, the structure that you see and the fact that it's not just, a pure circle is because of the gravitational interactions between these 2 stars. And actually, what we learned from this image for the first time is that the star that died actually still has dust around it. It's dusty, which basically means it either didn't expel all of its layers, which is which would be really unique, or it might be pulling material from the other star. Anyways, we don't know yet, but they're definitely interacting in more ways than just gravitational.
Wow, a lot of mysteries to unpack there. So that's really cool. We have Armed Camp on Twitter who asks, the pictures that we're seeing from the Carina Nebula, how old are they? And how many years ago did what we're seeing actually happen? Guess how many light years away was that nebula captured?
I don't have that off the top of my head.
Yeah, me neither.
That's okay. Armed Camp, that information is on nasa.gov in the web feature for that image. Yeah. But I think that does bring us to another good question. Can either of you put into context how big a light year is?
Sure. You all play with lasers, right? Like these laser pointers, right? So, if you point a laser pointer to an object that is 1 light year away, it will take 1 year for that ray of light to get there. So if you were trying to, share Wi-Fi with your friend at 4 light years away, it will take 4 years for them to actually get your Wi-Fi signal. So you don't really want to do that, right? It's a very, very slow process. But that's basically what a light year is. It's the amount of time that takes, it's the distance to which light can travel basically in 1 year. Yeah.
And to give you another sort of piece to measure it on, pun intended, the light travel time between the Earth and the Sun is 8 minutes, and that's 93 million miles. So 8 minutes into an entire year is a lot more than 83 million miles.
Yeah, I was like, I'm not even going to try to do that math. It is just a lot more.
It's a very large distance.
Yeah, that's good to know. We have Pyro on YouTube who asks, will JWST help us identify habitable planets. And so I know we've talked a little bit about how we can study the atmospheres, but we can study more than just water vapor, right? There are multiple different molecules. How does that all play together?
Yeah, so we're going through these questions through layers. The thing to understand is that our planet, in habitable conditions for our planet, are very far away from our host star, the sun. Because the sun is relatively hot to most stars out there. But the stars that we're going to be exploring with Webb, they're typically very cold. So in order to feel the same heat, just as a radiator, you have to get closer. So the planets that we're going to be studying that have what we call in the habitable zone, that receive heat similar to what we feel here on Earth from the sun, they're much closer to their stars. So the very first question is, do these planets retain their atmospheres? And the reason for that is because the stars, they are very much alive on their own, and they have, some of them are very active, and therefore, if the star starts to go a little bit crazy and have these spots, it's fine for us. Mostly telecommunications are impacted, but our lives more or less follow on.
Yeah.
But for these other worlds, if there's some activity in the star, then that might blow off their atmospheres even. So it's very dangerous to go there. So if you're thinking to go to the next habitable planet close by, please don't. Wait for us to investigate that first. But we want to figure out first if they have an atmosphere. Once we figure out if they do, next we start saying, okay, which elements does it have? So we go step by step, and then once we figure out what they're made of, then we can say, the atmosphere has conditions that might sound like what we call habitable here in the solar system. So if we found, for instance, like a very dense atmosphere like the one that Venus has, that's a place you don't want to go on vacation also. I'm thinking a ton on vacation because we've been 6 months in commissioning, right? So vacation is a very, very nice word in my mind. So depending on how dense or what molecules does these planets have, we might start getting closer and closer to what we call habitable. So that's how it goes, by layers, slowly, step by step.
Each layer sounds exciting, though.
Right.
So it's
Right.
going to be
Yeah.
great. We've got these observations in the first year. Everybody stay tuned. So our next question is from Documentary Library on YouTube, who asks, are the colors in the Webb images real? Basically, if we looked at them right now, is that what we would see?
No. They are false color images because the whole point of Webb is that it's what we can't see. Hubble has basically the same eyes that we do in visible wavelengths, but Hubble gives us a completely new view. In order for us as humans to be able to look at these, we translate the colors. So basically, we just, if you think of colors like what we can see, A, B, C, D, and then infrared would be E, F, G, H. And so we just say that, instead of E, it's now A. Mm-hmm. And we just take infrared colors, which are wavelengths, and we make them into visible colors with like our eyes. But if you look at an image, something that's red on the image is redder in space. So it's a real representation, but they are false color images because that's the only way that we could appreciate them. Otherwise, we'd show you a blank page and nobody would be very excited.
You'd be like, oh, okay, well, this is great. That's really where, the intersection, I kind of feel like science and art, we're weaving that together. So we have our next question from Minister of Casual on Twitch, who asks, is there anything we as the public with no background in astronomy can do to help contribute to analyze the images and data from Webb? Wow, that is a great question.
Yeah, I mean, well, there's different ways you can approach this, I guess. I mean, just by looking at the images, you will probably, and I've heard this from the public, sometimes they ask such great questions like, what is this? And we ask the experts, and the experts are like, I don't know. So you can figure out on your own. In the past, for previous missions, there has been some projects that have emerged as what we call citizen science. Mm-hmm. In which we put some challenges and we process a little bit the data, and then we show that data through the public, and then the public can also help. This is how galaxies have been discovered, planets have been discovered. So I could imagine that this same idea could be envisioned with a mission like Webb. What do you think, Alex?
Yeah, I definitely, I think that there's definitely citizen science projects in the future with Webb, and just supporting science so that, the work that needs to get done and these beautiful telescopes that need to get built are supported by our country, by our government, and so people who believe in and support science, and there's no reason not to believe in it because it's true, until we prove it wrong. And that's the beautiful cycle of science. Just supporting science is really the best that anybody can do. And as Nestor said, asking questions, those oftentimes lead to things we didn't even know we wanted to study.
So we have Sarge on Twitter who asks, can the general public request telescope time with Webb, and will the data be made available to the public?
Yes and yes. So anyone in the general public can propose. The next cycle for proposals there'll be an announcement made in the fall for people to propose to use next year's of Webb's time. And a lot of the data are already public today. And all of the data will be made public at least 1 year, at most 1 year after they are taken.
That is amazing. And I know actually we have 2 citizen scientists that have won time with the James Webb Space Telescope. So it's free, it's out there for the public. And so we'll move on to our next question from Dana, who on Facebook asks, how do you measure the distance of each galaxy in the deep field image?
Oh, that's an interesting question. We do it through the expansion of the universe, actually. We take advantage of this. It's a complicated thing, but we can take advantage of that. So what happens is that as objects are farther away, their light shows up to be a little bit redder than what we'd expect. And we have ways of figuring out, how red it has moved. So we can actually figure out from the colors first, and then from extra data that we can take on these objects, we can take this information and then convert it to a distance based on the expansion of the universe, which we know very, very well. Yeah.
Wow. Doesn't gravitational lensing play a part in this?
Yeah, so gravitational lensing actually helps us see even farther back because when you get a massive cluster of galaxies, their mass actually distorts space-time according to Einstein's gravitational laws. And so things that are behind a massive object, that light that may have gotten scattered outside of where we could see it actually gets bent towards us. And so they act like a magnifying glass for objects that are behind them, giving us access to more distant galaxies.
Wow. This is so cool. And so we only have about 1 more minute left, so this is going to be a quick one. But Alex on YouTube asks, what are some of the more anticipated discoveries that you believe the James Webb Space Telescope is capable of making?
Performing the first detection of an atmosphere around an habitable world. I mean, I would celebrate that. Whoever makes that discovery, if that's you, please go ahead. I mean, that would be fantastic. Yeah.
What about you, Alex?
Your pick.
I mean, for me, it's really star and planet formation. Looking into these beautiful stellar nurseries and peering back the dust, saying, yes, there is a star there, let's study it. And then being able to look at the gas, the dust, the star, and potentially even baby forming planets to see exactly what is going on.
Unfortunately, this is all the time that we have for today, but thank you both so much. This has been so fun, and just thank you for shining more light on these historic images.
Thank you.
And thank you to everyone tuning in today. I'm so happy we were able to answer so many questions and that we were able to just spend this moment together. We hope that you keep following the mission as Webb continues to peel back the curtain on the mysteries of the cosmos. To keep up with updates, follow NASA Webb on Twitter, Facebook, and Instagram. If you're on social media, be sure to check out our Instagram and Facebook filters. You can wear Webb-shaped sunglasses and take selfies in front of the newly released images. Now, if you want to go more in depth on the mission, visit go.nasa.gov/whereiswebb. Now remember, this is just the beginning for the James Webb Space Telescope. So be sure to keep following along as it unfolds the universe. Thank you, and see you next time.